Let us consider another example of the squid theorem. But before we do that, let us recall the squid theorem. It says that if we have three functions, f, g, and h, that are defined in an open interval containing a, except maybe possibly at a itself, and if the function values of g are always in between f and h, and if suppose we have a real number L such that the limit of f as x approaches a and the limit of h as x approaches a are both equal to L, then the limit of g of x as x approaches a must also be equal to L. Let us also recall the following trigonometric limit theorem. They are very useful when we are dealing with the limit of trigonometric functions. So let us consider the limit as x approaches 0 of sine of 2 pi x plus x squared minus x squared cosine of 2 pi x over x. This may look complicated, but let's try to do this step by step. So the first thing that we need to do is to apply the sum law or the addition law, where we distribute the limit to the addends in the function. So we have this form. Okay, so let's do sine of 2 pi x over x first. Let theta be 2 pi x. Why do we have to do that? We'll just have a placeholder. We'll define a placeholder for 2 pi x so that it will not be complicated or confusing later. Now, as x approaches 0, let's see what happens to 2 pi x. As x approaches 0, so we'll have the limit of 2 pi x. This would be 2 pi times x. So 2 pi times 0 is equal to 0. So we say that as x approaches 0, 2 pi x approaches 0. Since 2 pi x is theta, then we say that theta approaches 0 as x approaches 0. So this will be very useful later. Now, let us multiply the numerator and denominator by 2 pi. Why is this so? This is the same method that we used from the first example when we presented the squid theorem. Because the numerator is a sine function with an argument of 2 pi x, and our denominator only has x. So we need 2 pi x in the denominator. So we will multiply the numerator and denominator by 2 pi. So this gives us the limit of sine of 2 pi x over x times 2 pi over 2 pi. Then what will we do? We factor the numerator out of the limit since we don't need it. We only need the denominator. Okay, so that's what we did. We factored it out, and then the denominator is left inside the limit. So we'll have the limit of theta, the limit of theta approaches 0 of sine of theta over theta. Remember, theta was 2 pi x. Now this is now very easy to apply the theorem that we've learned earlier. We know that the limit of sine of theta over theta as theta approaches 0 is just equal to 1. So we say 2 pi times 1 is equal to 2 pi. So therefore, the limit of sine of 2 pi x over x as x approaches 0 is equal to 2 pi. Now we're not done yet. We only did the first addend. Now let's work on the second addend. But first, observe that we have a cosine function and the argument is 2 pi x. So basically, just like the previous slide, we let theta be 2 pi x, and we know that as x approaches 0, 2 pi x approaches 0. Hence, theta approaches 0 as x approaches 0, since theta is 2 pi x. Now, observe here in the numerator that we have a common factor that is x squared. So we factor it out from the numerator, and this gives us the limit of x squared times 1 minus cosine of 2 pi x over x as x approaches 0. then we apply the product law, meaning we will distribute the limit to the factors in the argument or in the function. So we get the limit of x squared times the limit of 1 minus cosine of 2 pi x over x. Then we multiply the numerator and denominator by 2 pi in the second addend, just like what we did before, since the argument of cosine is 2 pi x, so we need 2 pi x here. Or if you think that this is theta, then we should have a theta here. So for us to have a theta in the denominator, we need to have 2 pi x, but the given is just x, so we need 2 pi. Okay? Then we'll have the limit of x squared times the limit times 2 pi. The numerator here, we don't need the numerator, so we factor it out of the limit. That's why we have 2 pi here. Then times the limit of 1 minus cos of 2 pi x over 2 pi x. So this one is multiplied here. So let's continue. We know that, well, we see that 2 pi, we know that 2 pi is a constant, so we can factor it out of the limit. So we can rewrite this as 2 pi times the limit of x squared as x approaches 0 times the limit of 1 minus cosine of 2 pi x over 2 pi x as 2 pi x approaches 0. Now, this function or this limit, we already set or defined that theta, we already defined theta to be 2 pi x. So we can rewrite this in terms of theta. We'll have the limit of 1 minus cosine theta over theta as theta approaches 0. And we know that this is equal to 0 from the limit theorems. So therefore, when we evaluate the limit, we'll get 2 pi times 0 times 0. 2 pi is the constant. The limit of x squared as x approaches 0 is 0. And the limit of 1 minus cosine of 2 pi x over 2 pi x as 2 pi x approaches 0 is 0 from this. So therefore, we say that the limit as x approaches 0 of x squared minus x squared cosine of 2 pi x over x is equal to 0. So let's recall. We know that the limit of sine of 2 pi x over x as x approaches 0 is 2 pi. And that the limit of the second addend is 0. So therefore, when we use the sum law or the addition law, we'll have the limit of the sums. The sum of the limit of the sum is equal to the sum of the limit. So we have the limit of this is 2 pi, the limit of this is 0. So therefore, the limit of sine of 2 pi x plus x squared minus x squared cosine of 2 pi x over x as x approaches 0 is equal to 2 pi. Before we end, let me remind you of these important trigonometric limit theorems. So when your limit involves trigonometric functions and when they end up having an indeterminate form, then try to manipulate the function or transform the function in such a way that you are able to factor out these forms, any of these forms. Then after, you can evaluate the limit.